take a look at a system where complex eigenvalues crop up and how to deal with it. So we've got x1 prime equals minus x1 minus 6x2, and x2 prime is equal to 3x1 plus 5x2, and initial conditions of 2 for each of these variables. Okay, so this converts into a matrix system with coordinate matrix A given by minus 1, minus 6, 3, 5. And we've got an initial condition 2, 2. Okay, so let's see. So yeah, let me just label that. That's our coefficient matrix A. All right. So then let's see. So for eigenvalues, we will look at determinant A minus lambda I. And so this is going to be minus 1 minus lambda, and then minus 6 and 3 and 5 minus lambda. And this becomes lambda squared minus 4 lambda plus 13. And so this one does not look like it factors, so I resort to the quadratic formula. And so this is going to be 4 plus or minus square root of 16 minus 52 all over 2. So that's 4 plus or minus square root of minus 6. Minus 36. And so then that's going to be 4 plus or minus 6i over 2, or 2 plus or minus 3i. So we have complex conjugate eigenvalues. Let's look at the first one. So for the first one, we'll take 2 plus 3i. And when we look at A minus lambda times I, let's see, so we're going to get minus 3 minus 3i, and then minus 6, and then 3, and then 3 minus 3i. Okay, and so I can get rid of some constants here. So I'm going to divide, I guess, everything by 3. Actually, I'll divide the top by minus 3, so it becomes 1 plus I and 2, and then on the other side, 1 and 1 minus I. Okay, and now my usual tactic when dealing with stuff like this would be to multiply by the conjugate of the complex number in the column that I'm trying to clear out. But here, this one's simple enough that if I just multiply the second row by 1 plus I, then I can match this thing in the column up above. So I'll do that. And so this part stays as it is, and then I multiply the bottom one by 1 plus I, so I get 1 plus I. And then if I multiply this guy by 1 plus I have the square of the real part plus the square of the imaginary part, which is 2 again, which is great because I know it's supposed to work out where I get a row of zeros, or I computed the eigenvector wrong, right? So something like that. Okay, and so I can take v1 to be something like minus 2, 1 plus I. So I did the old switcheroo and then negate one of the entries. Okay, now for lambda 2 equal to 2 minus 3i. So this one is the conjugate of lambda 1. And so v2 is going to be the conjugate of lambda 2, which means that just like I went from here to here by negating the imaginary part, I can do the same thing for the other one. So let me see. So v1 was minus 2, 1 plus I. So to negate the imaginary part, I just make that bottom one a minus sign there. So just for emphasis, I'll make it purple. And that will work as an eigenvector. So remember, if A is all real, so no complex or imaginary entries, then then so if V is a lambda eigenvector, then conjugate V will be a conjugate lambda eigenvector. Okay, so that's the shortcut there. So, okay, where does that put us? All right, so if we look for our first eigenvector, then we're going to have e to the 2 plus 3i t times minus 2 1 plus I. And we have to figure out what to do with this. So we go to Euler's formula, which says that I can split this into e to the 2t cosine 3t plus I sine 3t. Okay. And so now if I have e to the 2 plus 3i t times negative 2, 1 plus I, this is going to be e to the 2t, and then I'm going to have the cosine and the sine multiplied in here. So across the top I have minus 2 cosine 3t minus 2i sine 3t, and then across the bottom I'm going to have cosine 3t plus I sine 3t, and then the part multiplied by I, so I cosine 3t, and then I times I sine is minus sine 3t. So we have that one. And what I'm doing right now is I just want to collect the I terms. So I have them now located here and here. So I want to put those guys in a vector by themselves. So let's see. So I've got e to the 2t, and then and I forgot the that guy. So I'm going to have the real parts, minus 2 cosine 3t, and then cosine 3t minus sine 3t. Okay, that's all the real junk. Plus I e to the 2t, and then I've got all the imaginary parts. So there was a minus 2 sine 3t, and there was a sine 3t minus cosine 3t. Okay, and so key point is I've managed to consolidate all of these i's into just this one right here. Okay. And so now I have two linearly independent solutions, and so I can take this one here as my x1, and this one here as my x2. So that's great. So let's see. So then my general solution will be c1 e to the 2t 2 cosine 3t cosine 3t minus sine 3t, and then c2, and I just sweep that complex imaginary I into the c2. And there we go. So you might be kind of surprised because we started off back here saying, okay, here's our x1, and then that actually turned out to be to give us both x1 and x2. But that's fine. That's just one of the beautiful ways that complex numbers work. So it's simplified actually for us. Okay, so last step is to take into account the initial conditions, and so let's go ahead and do that. So we have initial conditions of 2 and 2, that's our x0. And meanwhile, for x0, we can also evaluate this whole thing right here at t equals 0. And so let's see. So those exponentials are both going to become 1. And so we have c1 times 2, 1, and c2 times 0, minus 1. And so we're looking to solve the system that looks like minus 2, 0. Oh, wait, 2 or minus 2. Oh, typo. I lost it. Okay. Yeah, typo right here. There should have been a minus sign in front. Okay, yeah. And then this would be a minus sign here. Okay. So that was also a typo. Okay, back on track. So we have minus 2, 0, 1, 1, 2, 2. And we reduce that system. And we find minus 1, 3. So there's our C1 and our C2. And so then that tells us that the solution to the initial value problem is given by, let's see, so we've got minus e to the 2t times negative 2 cosine 3t, cosine 3t minus sine 3t, and plus 3e to the 2t minus 2 sine 3t cosine 3t plus sine 3t. And from that, we can see that x1 of t is 2e to the t cosine 3t minus 6e to the 2t sine 3t, and x2 is let's see, so I'm going to have minus 1 of them and plus 3 of them, so I'll have a grand total of 2 of them, 2e to the t cosine 3t, and then I'll have positive 1 sines, and then so then total of 4. There we go. And so there's the solution to that system that we started with.